Okay, very good. Thank you, Luis. And it's a real honor to be asked to give this this last talk of a really wonderful conference. I apologize, and I really wish I could have been there. I enjoyed the venue there very much, and I was looking forward to it. And unfortunately, the visa issue just turned out to be insurmountable. So I'm going to have to rely on the participants who are there to give a big round of applause for Sushmita and Nuno for organizing this wonderful event. Hopefully there are claps in the background. I can't hear them, but okay. All right, so please feel free to ask questions. Hopefully there's a microphone so that I can hear questions if they come in. But I'm unfortunately not going to be talking about vortices so much, but about Higgs bundles. So I wanted to give a talk more on vortices, but that work is not quite ready yet. So I'd like to talk about something else that we've been doing that's almost finished now. So and this is joint work with Brian Collier and Laura Fredrickson on something called conformal limits. So let me begin with the sort of work that's already been done, and then I'll get to the main new topic, namely the application to parabolic Higgs bundles. Okay, so let me just start with notation. So C is going to be a compact Riemann surface of the usual genus assumptions here. So we have three moduli spaces that we're interested in. One is the moduli space of bundles, then the moduli space of Higgs bundles, which is sometimes called the Dolbeault moduli space, and then the moduli space of flat connections or holomorphic connections, which is sometimes called the de Rham space. So these are all, I'm only interested in stable objects here, so these are all complex manifolds. Both Dolbeault and de Rham have the same dimension, and that dimension is twice the dimension of the moduli of bundles. So to give some idea of the structure of these things, I'm sure many of you are familiar with it, but let me just kind of say some basic things. So there are open sets inside of these moduli spaces that fiber over moduli of bundles. So inside of the Dolbeault moduli space, there's an open set which is identified with the cotangent bundle of the moduli space of vector bundles. And on the de Rham side, there's also an open set which maps onto moduli of stable bundles. But this is not the vector bundle, it's just a torsor over the cotangent bundle. Okay. And so then the most important thing that you know about these moduli spaces, the Dolbeault moduli space, the Higgs bundles moduli space, and the flat connections, is that there's something called the non-abelian Hodge correspondence, which is a diffeomorphism between the two moduli spaces, Dolbeault and de Rham. So I'll review that very briefly later on, but this is just think of it as some diffeomorphism. It's not complex analytic. And now if we look at these open sets that I just described down here, then this diagram that I've drawn doesn't commute. And in fact, non-abelian Hodge doesn't even preserve these open sets in general. So non-abelian Hodge doesn't, non-abelian Hodge doesn't act nicely with respect to these mappings. Okay, so we could try to fix this. So there is actually a commuting diagram, sort of almost a trivial one. Well, not really trivial, but it comes from the Narasimhan-Seshadri theorem, which gives you a section of the de Rham moduli space. And then that turns this torsor into a vector bundle, which is then identified with the cotangent bundle. This is a non-holomorphic identification. It is, of course, mapping fibers to fibers, so it's holomorphic on fibers. Overall, it's a non-holomorphic fibration, but it does take this open set diffeomorphically onto this one. So the conformal limit can be thought of as an extension of this to the full moduli spaces. So there's a technical point, but it's not defined completely everywhere, but let's not worry too much about that. it's defined almost everywhere, and it extends this map that we've defined here to the full moduli space, essentially the full moduli space. And it's a very strange map. It's not continuous, but it does interchange two natural stratifications on the two moduli spaces. So I want to just kind of review what that is. So we've already seen one stratum, namely the open one. So this has a stratification. We'll see from a C star action, and this stratum here, the cotangent bundle, is the open stratum. And similarly over here, there's an open stratum. And this identification I've sort of indicated from Narasimha Seshadri is this identification on the particular open stratum. But the full conformal limit extends that to all of the other strata as well. So at the other extreme, there are the closed strata. And in the Dolbeault moduli space, those are known as Hitchin components. And in the de Rham moduli space, those are known as opers. And the original conjecture of Gaiotto in a paper in 14 was that the conformal limit, as he defined it, and I'll define in a little bit, should give an identification between these two, between the closed strata in the moduli space. And that was proven in a joint work of several authors here after an AIM conference where they discussed this conjecture. And so the result is that the conformal limit, again, I haven't told you what that is yet, but I will in a second. The conformal limit on each Hitchin component, first of all, exists, and it gives a biholomorphism between the Hitchin components and the Oper components. And then later, Brian Collier and I generalized that, and we sort of realized that this was really a more general statement, and it really applies to all of the strata, not just the closed strata and not just the open strata, but all of the strata of two natural fibrations of the moduli spaces. Okay, so so the plan of my talk is to, because this is probably not super familiar to everybody, so I want to define this and sort of describe this theorem a little bit more generally, and then move on to talk about what we've done next, namely the parabolic bundles case. So this was for closed Riemann surface. The original conjecture of Gaiotto actually was for punctured Riemann surfaces, and so that's what we want to generalize. Okay, so first of all, are there any questions? Okay, I don't hear anything. Hopefully that means that there aren't any questions and not that my audio is not working. Okay, so let me review then a little bit about Higgs bundles. I think everybody really knows this stuff, but let me just do it anyway. So Higgs bundle is a pair of a holomorphic vector bundle and a holomorphic endomorphism valued one form. On the other hand, a flat connection I'll write as this, namely a holomorphic bundle. I always think of a holomorphic bundle as being identified with a d-bar operator, an integrable d-bar operator, and then an algebraic connection. So so here I'm thinking this is really a map of sheaves. So the holomorphic sections of V get mapped by the connection satisfying a Leibniz rule. Okay, and the non-abelian Hodge theorem, again under some assumption of stability, says that there's a Hermitian structure that makes these two objects get identified. So for every stable Higgs bundle, there's a harmonic metric that gives you a flat connection under this identification, and vice versa. Every flat connection has a splitting with a harmonic metric that gives you a Higgs bundle in this way. So this is how the two are identified. Okay, so another way to say this is that, as I said, so given a Higgs bundle, we get a flat connection by this identification, and then you'll notice it's slightly more general than that. You can also scale the Higgs field, these two components, and get a flat connection, a whole family of flat connections this way. And this kind of freedom to do a scaling is sort of a reflection of the hyperkähler structure. And indeed, these families can be regarded as sections of the twistor space associated to the moduli space. And if we restrict that twistor space over the complex numbers, then this has another meaning. And it's another moduli space known as the Hodge moduli space, which is not important for us, but I just want to say that we can think of this family as being non-abelian Hodge as giving us a holomorphic section of the twistor family associated to the moduli space. Okay, so the other ingredient that's very important in this whole business is that there's a C-star action. It just comes from scaling the Higgs field. And the limits of the C-star action always exist. So of course we have to complete the moduli space, so let's not worry too much about that, but the limit always exists, and this gives you as we'll see later, a stratification of the Dolbeault moduli space. And the fixed points of the C-star action are what are known as Hodge bundles. So of course, if phi is identically 0, that gives you a whole family of fixed points, and that's just the moduli space. That component is just what I called N earlier on, the moduli of stable bundles. But there are other fixed point loci, and those are called Hodge bundles. And then one other little note here is that the C-star action extends over the twistor space to cover the usual action on P1, in particular over C. Okay. So what I'm trying to emphasize here is that on this twistor space, there's sort of two things going on. There's a C-star action that's going to take points in this twistor space to other points over the fiber 0. And then in addition, there are holomorphic sections of the twistor space for every point in the 0 fiber. Okay, so those are two seemingly very different structures. So let me just recall what a Hodge bundle is. So we already saw the Hodge bundle for phi equals 0. What is the general situation? So the general situation is that the underlying holomorphic vector bundle is holomorphically split, and the Higgs field just maps the various components to the next one. Okay. So what is the analog of this in the de Rham side? A priori, there is no analog, but you can ask, so these are the Hodge bundles, so that means that there are going to be, these are going to be limits of ordinary Higgs bundles as that C-star action goes to 0. We can ask the same thing on the de Rham side. If I have a flat connection and I act on it by C-star, first of all, does it have a limit? And if so, how do I understand what that limit is? And so this was done by Simpson. So let's introduce some notation. So if we have a flat connection, so I'm thinking of V now as a holomorphic bundle with an algebraic connection, then we can look at filtrations by subbundles. And we'll say that this is Griffith's transverse. This is sort of coming from classical Hodge theory. This is Griffith's transverse if, first of all, it maps one element of the filtration to the next one up. And instead of dropping an assumption on an isomorphism, we just lose that assumption and just examine what the flat connection induces on the various associated graded pieces. So, so notice that if I look at, because of this condition, if I look at that, if I look at the connection on these associated graded pieces, then this is tensorial. The Leibniz piece drops out of this precisely because the Leibniz piece still lives in V1, and we're quotienting out by V1 here. So this is actually a homomorphism of sheaves. And that's exactly of the type that the Higgs field is exactly of this form. So in other words, we get potentially a Higgs bundle given a Griffiths transverse connection, filtration on a flat bundle. And so Simpson proved that if you have any flat bundle, then there's a Griffiths transverse filtration such that the associated Hodge bundle is semi-stable. And so here, of course, we're interested in the case where it's stable. Again, let me not worry too much about those subtleties right now. In any case, this filtration is essentially unique. Okay, so this gives you kind of a stratification then of the de Rham moduli space, but in particular the Hodge moduli space. So he proves that every point in the Hodge moduli space has a limit, and of course this limit has to live over the fiber over 0, and indeed it's a Hodge bundle. Okay, as usual with slides, I'm going a little bit faster than I like, but please feel free to stop me if you have questions. Okay, so maybe I'll just give one example. This is the example that everybody's kind of familiar with, I think. So one of the most important examples is this one. So we take a root of the canonical bundle if necessary, and we take this direct sum. And then there's an obvious Higgs field associated to this, namely because we're taking powers of the canonical bundle that increase exactly by 1. The next factor here, tensor by k, is naturally isomorphic to the previous one, and so we can take as our Higgs field just the identity on those components. So there's sort of a natural Hodge bundle staring at us whenever we do this construction. Similarly, there's a flat connection, a flat bundle, which is just the jet bundle of the canonical bundle now. So if you like, that's a sequence of non-split extensions of these powers of the canonical bundle. I successively do non-split extension. And that one has a natural flat structure. In fact, it has a whole family of flat structures. But there's one that comes from uniformization, namely we're on a Riemann surface, so we know that it has a uniformization, and that gives you a natural projective structure. And if we take the symmetric power of that projective structure, we get a flat connection on a rank n bundle, and that's that rank n bundle is exactly this jet bundle here. So this is sometimes called the universal Oper. So these two correspond, in other words, under non-abelian Hodge, and they also correspond under this Simpson correspondence that I had on the previous slide. Namely, if I take the associated graded of this Oper, then I recover this Hodge bundle. Okay, so this is a situation where the construction that I just described using Griffiths transverse filtrations gives you a Hodge bundle, and it gives you exactly the Hodge bundle that corresponds under non-abelian Hodge correspondence. But we'll see that this is not true in general. This is only true of the Hodge bundle in general. Okay, so finally, let me state what these stratifications are then. So let's fix a Hodge bundle. We fix a fixed point of the C star action, and we want to look at the, in the Morse theory sense, the stable manifold of this. So everything that flows into this under the C star action. So on the one hand, we can look at that on the Dolbeau side, and on the other hand, we can look at it on the de Rham side. So those are two objects. Okay. So here I've defined it just as I said. So I'll just call these W0 and W1. Probably not the best notation, but the W0 one is in the Higgs bundle moduli space, and it's just all the Higgs bundles that limit to this fixed Hodge bundle. And then on the de Rham side, again, this is Simpson's limit. In other words, these are all the flat connections whose Griffith's transverse filtration has this Hodge bundle as its associated graded. Okay, that's the way to think about it. So we just saw one example, namely where this was the uniformizing Higgs bundle, and then inside of this we saw the uniformizing Oper. Okay, but then we have a whole strata there so in the particular case, I should just say also, in the particular case where phi was 0, then we just recover the tangent bundle, the cotangent bundle here on this side, and then this other fiber that I described, this open set on the de Rham side. Okay, and the important fact, I guess, is that in general, non-abelian Hodge does not take one stratum to the other. It does on the particular Hodge bundle, that's what we just discussed, but in general, it's just not true. Okay. And so the conformal limit is something that's going to take the strata to the strata. So this is Gayota's idea, and of course I should say that you know, I'm attributing this to Gayota. He did have the original ideas. His motivation was completely different, and I'm not qualified to really say very much about what his motivation is or was, but I'm sure that there are people in the audience who know much more about this than I do. So I'm sort of perverting his motivation into a more geometric one, the way I think about it. But in any case, his idea is to combine these two actions on the Hodge moduli space that I mentioned, namely the twistor line with the C star action, and move along those two holomorphic sections in a way that is proportional. So again, here, what am I doing? I'm on the one hand, I'm scaling the Higgs bundle. This is the C star action. Here, I'm just scaling by real number, but you should think of that as being the C star action on the Higgs bundles. And then the C is going out along the twistor line. And the idea is that you want to look at the family of flat connections that you get by doing those two things, those two operations in a fixed proportional manner. And of course, Gayota being a physicist, there has to be an H bar somewhere, so that's where the H bar comes in. But from now on, I'm just going to set H bar equal to 1. Okay, so this is the family of flat connections that we get, again, just by some proportional combination of the C star action with the twistor line. And so we could ask what happens as R goes to 0. What happens when we take the limit of these things? So, and if it exists, then this is what is called the conformal limit. Okay, so exists inside of M de Rham, in other words, when H bar is equal to 1. So notice that I'm not saying the limit up to gauge. This is really the limit of the flat connections. This is not up to gauge. And so what we proved, so now I'm restating the theorem that I stated earlier, but in slightly more detail, is that as long as this Hodge bundle is a stable Hodge bundle, it's as stable as a Higgs bundle, in other words, which is an almost everywhere kind of condition, then the conformal limit indeed exists. and it lies in this stratum W1. So in other words, it gives you a flat connection whose associated graded recovers this as its Hodge bundle. And in fact, this gives you a biholomorphism between the fibers in the Dolbeau moduli space and the fibers in the Dural moduli space. So this is a complete generalization of the earlier example of the cotangent bundle and the tangent bundle. Notice here I'm looking at just the fiber over a fixed Hodge bundle. I'm not looking at a whole locus. So I'm just identifying the fibers, and that's a biholomorphism. We've already seen as we vary within a given component of the Hodge bundles, then this identification is not likely to be holomorphic, but it is on each fiber individually. All right. So that's the old theorem. And okay, so maybe I should say a little bit about what this is. So how this comes about. So it turns out that the conformal limit is actually very, very explicit. So again, we saw that in the example that I gave. You do have to solve one thing, namely the Narasimhan-Seshadri theorem says that a stable bundle gives you a flat connection. Happens to be a unitary connection, but then I can take a complex connection by adding any holomorphic one form to that. And so that's how it works in general. But the question is in the other strata is what exactly are you adding? And that's what comes from a certain gauge, a very natural gauge fixing kind of setup. So let me just describe this a little bit because I think it's maybe a little bit less known and maybe more interesting. So first of all, when we have a Higgs bundle with a harmonic metric, so here I'm writing the flat connection that we had before, but dividing it up into this natural way that Simpson often does. So these are the sort of the holomorphically varying things, even though they're of different type on the Riemann surface. These are the two holomorphically varying objects for a moduli space. And then we take the adjoint of those. Okay. So we have these two operators constructed out of the harmonic bundle. So now consider a pair of equations where I look at deformation. So I want to deform the holomorphic bundle that's given by a 0-1 form, and I want to deform the Higgs field that's given by a 1-0 form, and they should satisfy these two equations. Okay, so here I just mean apply this operator to beta and phi. Okay, we're on a Riemann surface, so it really only applies this. This is what hits beta. Sorry, this is what hits phi. This is what hits beta, and vice versa over here. Okay, so in any case, we have these two equations with this commutator phi as well. And what did I want to say? Right, so what is this first equation? This first equation, if you work it out, is just saying that when I add beta to the d-bar operator and I add little phi to phi, then I get another Higgs bundle, namely that this new field is holomorphic with respect to this new d-bar operator. Okay, that's just very simple calculation there. And the second one is sort of the natural gauge fixing condition that we would impose on the tangent space. If we want to look at the tangent space of the moduli space, we have to fix the gauge. And I claim that this is a very natural gauge, choice of gauge. And indeed, at least when the underlying bundle is stable, then looking at all solutions to these two equations, this is an elliptic system, so we get a finite dimensional manifold. At least we get a finite dimensional manifold, at least in a neighborhood of the origin, and that is indeed a slice for the action. So this gives us a local coordinate system on the moduli space of Higgs bundles. In other words, this is how you construct the complex structure on the moduli space of Higgs bundles. Okay, but because of this very nice choice of gauge, in fact, there's a natural parameterization of flat connections at the same time. So by doing the most trivial thing, namely just taking the original flat connection here and adding these two. Okay, so the same slice gives you a local coordinate both in the Dolbeault and the de Rham moduli space. Okay. So, and this is interesting because non-abelian Hodge, right? I mean, is a very non-holomorphic correspondence between those two moduli spaces, but these sort of the infinitesimal version of non-abelian Hodge sort of naturally gives rise to this slice, which is a local coordinate, a local holomorphic coordinate for both. Okay. So notice in the open stratum case, beta was just 0, and so indeed we were just adding phi. And this condition, when beta is 0, just amounts to holomorphicity of phi. Okay. So this slice, in other words, was just the cotangent bundle to the moduli space, the fiber of the cotangent bundle to the moduli space of stable bundles at this particular holomorphic structure. Okay, so so now the point is that, okay, so now I should describe this. Now I'm going to say what the conformal limit is. So suppose we have a general Hodge bundle. And so I just remind you what that is. It's a splitting of the holomorphic bundle in a Higgs field of a particular form like this. So then in the deformation complex for the tangent space at this particular point in the Higgs moduli space, then you see a natural subcomplex that appears, and that gives rise to a subslice that corresponds, roughly speaking, to upper triangular deformation. So beta is strictly upper triangular, phi is upper triangular with respect to the natural filtration that comes here. And this gives us a subslice of the one that I described on the previous slide. And in fact, this slice gives you this slice is biholomorphic to the entire fiber. So I don't know if I used this terminology earlier, but the entire C star fiber, if you like, over this fixed Hodge bundle. Okay, and notice that this is a global statement. So before I just said that slice locally gives you a coordinate on the moduli space. This sub-slice is actually globally biholomorphic to the entire fiber. Okay, so we really identify it with the entire fiber. But now that naturally maps also into the de Rham space by this correspondence that I said before, and it turns out that that's exactly the conformal limit. That takes this slice in the de Rham moduli space that is identified with what I call W0. I should have written that here. Sorry. This is identified. This statement here is identifying the slice with W0, and the map to W1, the biholomorphism, is just this easy correspondence here that we've obtained. And that's what the conformal limit is. So it sounds almost trivial. There's not much work, but indeed, we do have to prove something, namely that family of flat connections, the way that conformal limit was originally defined, we have to prove that really does map to this particular flat connection. And to do that, we have to understand the non-abelian Hodge. We have to understand how the harmonic metric varies as we scale along the C star action. The harmonic metric in general blows up as R goes to 0, and so one has to understand that blow up, and that's exactly the argument really that was given in this original paper of these guys, and that same argument pretty much applies word for word to our situation as well. So that's how the conformal limit works, and the nice thing is that it's something very, very explicit, in other words. Okay, any questions? Yep. Okay. Right. So now I have I think the right amount of time to maybe say a few words about what we're doing, what the new work is. So as I mentioned, yes.
Mic to work.
Yeah, I do. And then you wait. Hello. Oh, just one question. Can you remind me what the BB vibration is?
Yeah. So this is just the collection, the vibration that the fibers. Well, this is more general. So the moduli space of Higgs bundles is a quasi-projective variety. There's a C-star action and the limits as lambda goes to 0 always exist. In that context, you have a natural stratification, a holomorphic stratification of the moduli space. And those are called the BB, that's the Bialynski-Berula stratification.
Okay. Yeah, in a sense.
That's the one I'm referring to. What I call W0 are the individual pieces within that stratification. So they're not the full strata, because the critical sets in general are not isolated. So they're not the full strata, but they're just the individual stable manifolds of critical points, fixed points of the C-star.
Thank you.
And notice that on the Durham side, you don't have anything like that. You don't have a C-star action on the Durham side. That's what the Simpson stratification is sort of replacing. All right, any other questions?
No.
Okay.
That's it.
Good. All right. So Gayota's original conjecture was for what we would call Higgs bundle with parabolic structure, or even wild parabolic structure. So I'm not going to say anything about wild Higgs bundles, just classical parabolic bundles. And so we wanted to generalize to sort of make real contact with his paper. We wanted to generalize this theorem for parabolic bundles. So this is a little briefer on parabolic Higgs bundles. So what is a parabolic structure? So unfortunately, I'm using D now for divisor, whereas it was a flat connection before. Sorry about that. So this is just a reduced effective divisor on the Riemann surface, namely a collection of distinct points. And if I have a holomorphic bundle, then a parabolic structure on that holomorphic bundle consists of the first two objects, namely a choice of flag and a fiber at every point over P, and a choice of weights that are just simply numbers, real or rational if you prefer, between 0 and 1, weighted in this way. And here, the number of weights has to correspond to the type of the flag. Okay. So a full flag would have n weights, namely the rank of the bundle, and the other parabolics will have different numbers here. Okay, so that's what a parabolic bundle is. And a parabolic Higgs bundle has also a Higgs field, where the Higgs field now is allowed to be meromorphic with simple poles, and with the condition that the residue preserves the flag. Okay, so the residue of the Higgs bundle then is, of the Higgs field is a well-defined endomorphism of the fiber, and that endomorphism should preserve the flag. Okay, so Simpson, of course, proved in a very famous paper, proved the non-abelian Hodge correspondence in this context as well. And on the de Rham side, what you obtain, of course, are logarithmic connections, also with a parabolic structure, and or maybe sometimes they call this a filtered structure, and that's a better way to say it. But in any case, we can think of it as a parabolic structure, and the residue of the algebraic connection here, the logarithmic connection, the residue of the connection is also an endomorphism of the fiber, and that should also preserve the flags. Okay, so so there are sort of two kind of flavors here. One is what is known as strongly parabolic. So that's if the residue of the Higgs field is strictly upper triangular with respect to the flag structure. And in this case, on the moduli space of such objects, we still have a C-star action. If we wanted to fix the residue to be something else, to have eigenvalues, then in principle, you wouldn't have a C-star action. So then we have to consider all possible residues. Then the C-star action exists on that moduli space again, but it's a more complicated object. So let me just say right from the very beginning that we have to make an assumption here. So we're either going to restrict to the strongly parabolic case or the more general case, but in that case, we need to assume full flags. In fact, I don't know what those moduli spaces are, not in the full flag case, but in any case, that's going to be our assumption. Okay. And okay, so this more general moduli space has been discussed in several papers, in particular Yokogawa, who did it even in higher dimensions, and a very nice paper of Logares and Martins talks about this extended moduli space of parabolic Higgs bundles. Again, I'm talking about the case where you allow for arbitrary residues, arbitrary eigenvalues for the residues. So this extended moduli space, I should have mentioned David Alfaya here as well. Sorry. This extended moduli space then of parabolic bundles. Again, I'm assuming full flags here, and so in that case, at every point, I can look at the eigenvalues. So here I'm just writing this as traceless diagonal matrices for some reason. So this is the more direct map that we have at every point. So the 5/0 here would be the strongly parabolic moduli space sitting inside of here. And the C-star action covers the C-star action here. So the C-star action in general only preserves that, well, it only preserves that fiber. Okay. All right. So one thing that we needed to do, yeah, I should now speed up a little bit. One thing that we needed to do was, and we do this, is give a gauge theoretic construction of this moduli space. So the algebraic constructions exist by these authors, and I should add David Alfaya, sorry. So, and probably others that I'm leaving out, sorry about that. And so we give a gauge theoretic construction. So this is using techniques that have been around for a very long time, developed originally, I think, by Tauds and Moravka, based on an influential paper of Lockhart and McCollum. And then developed further for Higgs bundles, especially in the strongly parabolic case. So maybe the only original thing here is that we're kind of looking at the general, not strongly parabolic case, but we add for these other weights. Okay, so this is a gauge theoretic construction of these moduli spaces as complex manifolds. Okay, and we really need that to do the slice construction and make the conformal limits. So the idea is something that we saw in Sushmita's talk. For the punctures, I want to think, you don't have to do it this way, but for me, this is more convenient. I want to think of the puncture now, blow out the puncture to a semi-infinite cylinder, and start with a model connection, which is adapted to the parabolic weights. So the parabolic weights give us a particular flat connection on this cylinder with holonomy determined by these weights. Okay, so I start with a model connection of this type, and then I define Sobolev spaces by weighting the usual Sobolev spaces. This means K derivatives in L2. L2 is enough for us. Weighted the K derivatives in L2, but we take all of the norms weighted by this particular function. So the coordinate tau is just the real coordinate going to infinity here, and then I just extend tau to be an arbitrary smooth function. I don't really care how. And then we weight all of the norms by e to the tau delta. And the choice of delta is very important. It's determined. It has to be sufficiently small depending upon the particular choice of weights here. Okay, and then the connections that we're going to be using, the unitary connections in any case, are going to be decaying to this model connection. More precisely, it's the model connection plus anything that lives in one of these L2 delta spaces. So the way you should think about this is that this connection is in some sense, it's decaying to this model connection as tau goes to infinity. Okay, and now for the Higgs field, we allow some growth actually for the Higgs field. So it's convenient to take it to be an L2 minus delta. These spaces make sense for minus values of the weight as well, negative values of the weight as well. And so we define a sort of what looks like a funny domain. So we take a priori, we look at all phis in L2 minus delta, but so that the derivative with respect to the connection lies back in L2 delta. So the derivative here would naturally be in L2 minus delta. Here we only look at the ones that live in L2 delta. So that defines some domain, and that's going to be the domain for our Higgs fields. Okay, and indeed, this is the right kind of setup. So if we have a Higgs bundle, so now I impose that this is this guy is holomorphic with respect to d bar A, then indeed that recovers for us a parabolic Higgs bundle. And the point about taking minus delta here is that allows for the possibility of the eigenvalues of the residue of the Higgs field to be non-zero. Okay, so this gives you a construction of the moduli space. So now where did the full flag assumption come in? I just want to point this out. And I'm going to go a little bit over because I think I started a little bit late. So the full flag assumption is really jumps out from the analytic construction because there are nonlinear terms here, and in particular terms that look like commutators of this type that you're familiar with from Higgs bundles, where I have to take the commutator of these two objects. And all of these things should live in the correct space. So in particular, this should be an L2 delta. Okay, and in general, this does not seem to be true. If all of this makes sense in the general setup, but this object here, this commutator, and other nonlinear terms that appear when we do the analysis do not seem to be an L2 delta in general, but they are if we make the assumption of full flags. So the full flag assumption really is a very natural one from the point of view of the analysis. Okay, so in that case, the same method gives the construction of the moduli space, and the non-abelian Hodge correspondence, as I say, has essentially been proven by Simpson, but in this context, maybe Picard's work is more relevant in this weighted Sobolev context. In any case, we get a correspondence between elements of the space here, the parabolic Higgs bundle space, and an analogous one that we construct on the de Rham side. Okay, so the same kind of construction will work for flat connections. All right, and so then the theorem, finally, this is really my last slide. So the theorem is my second to last slide, sorry, is that everything goes through. So again, we have two stratifications. Now the C star action is on this bigger space where we don't fix the residues. But again, there's a notion of strata. The fixed points are again Hodge bundles, and we get the conformal limit existence theorem and correspondence of strata, much like we had before. And there are examples. Unfortunately, we haven't completely figured out which examples in Gaiotto's paper really are covered by this construction. We have lots of examples in mind, but we just haven't written down all those details yet. So I can't present concrete examples, but certainly on P1 with 4 punctures, there are some very nice examples, explicit examples of what this correspondence is. So for my last slide, let me just point out something that, so people there who are familiar with Simpson's work know that there's a very interesting table about how the residues behave under the non-abelian Hodge correspondence. So here, this is the Higgs bundle side. This is the flat connection side. I said that the flat connection is a logarithmic connection. It has a residue. These are the eigenvalues of the residue. But I also said it was a parabolic structure, but the weights are different in general. the weights of the parabolic structure for the flat connection differ from the weights of the parabolic structure on the Higgs bundle side, depending upon turns out the real part of the eigenvalue of the Higgs field. Okay, so there's a very interesting correspondence here that SIPS implies. In the conformal limit side, it's completely different. On the conformal limit table, the parabolic structure is the same on both in the conformal limit. And similarly, you have a different sort of change in the eigenvalues. So the residue of the flat connection that appears in the conformal limit is also different from the residue of the one that appears in the non-abelian Hodge correspondence. So in some sense, if you think about it, the conformal limit is a much simpler construction than non-abelian Hodge. But at the same time, it's sort of more suited to this C-star stratification. Okay, so that's I think all I wanted to say, and just another round of thanks to the organizers for a wonderful conference.
So questions or comments? The questions online? Maybe I can this conformal limit bijection that you explained in the first slide without parabolic structure, does it work in higher dimensions?
That's an interesting question that I've not thought at all about. That's a very interesting question. I'm sorry, I haven't thought at all about that.
The rest should only be workable in dimension 1.
Right. Yeah, I'm sort of at a loss for words. I don't know. I don't know what to say. I'm completely agnostic about what that is. But you're right. A priori, I don't see why one couldn't ask the same sorts of questions in higher dimensions.
Okay. Yeah, I guess the examples of operas are more in dimension 2. And
sure.
Maybe that's part of related.
But with the appropriate Chern class kind of construct restrictions, then you ought to have you still have the non-abelian Hodge correspondence and
yeah.
what the analog of the conformal limit is.
Mm-hmm. And there is no chance you can construct with these gauge theoretic methods the moduli of parabolic bundles for more general parabolic structure.
Yeah, I'm very confused on that point. I really don't know what's happening. So already in this map here, you would have to divide by in general, this map would only go to the quotient of this by the action of the levy on its Lie algebra, which doesn't look like a very Hausdorff object in general. And so I'm not even now. I guess that doesn't necessarily mean that there's not a good Hausdorff construction in the moduli space, but I'm a little bit confused about how to construct that moduli space even algebraically.
There is no algebraic construction?
I think there is. You see, so I think it's my confusion, not a confusion in the literature. But what I find interesting is that it really pops out analytically the difficulties as well. So analytically, I really think that there's something else going on. So and there's another reason. I think that I don't know if Oscar is still there, but he can certainly tell you about this. But there's another reason that things will go wrong, and that is that let me just say this briefly. So I said that there's a model connection here, right here. So here, implicitly, there's a unitary frame as well. So in other words, I've chosen a metric and the metric is adapted so that my model connection looks like this. When you have general residues for the Higgs field in non-abelian Hodge, that metric will not actually work. The model metric you choose has to be adapted. There are logarithmic terms instead of just powers of tau that appear in the decay of the harmonic metric. There are also logarithmic terms coming from the Jordan type of the residue of the Higgs field. And so, and that depends on the residue of the Higgs field. And I don't understand how you would do this gauge theoretically, because as you move around in the moduli space, that model metric would have to move. And that sort of violates, you know, every gauge theory construction I know of. So I'm quite confused about how to do this in the non-full flag case, actually.
Let's see. Okay. More questions? Okay, then let's thank Richard again.